Class hierarchies. C++, abstract mechanisms. The container example is a very simple example of a class hierarchy. A class hierarchy is a set of classes ordered in a lattice created by derivation, example, public. We use class hierarchies to represent concepts that have hierarchical relationships. Such as, a fire engine is a kind of a truck which is a kind of a vehicle, and a smiley face is a kind of a circle which is a kind of a shape. Huge hierarchies, with hundreds of classes, that are both deep and wide are common. As a semi-realistic classic example, let's consider shapes on a screen. Smiley, circle, shape, triangle, shape. The arrows represent inheritance relationships. For example, class circle is derived from class shape. To represent that simple diagram in code, we must first specify a class that defines the general properties of all shapes. Class shape. Public. Virtual point center, const equals 0, pure virtual. Virtual void move, point to, equals 0. Virtual void draw, const equals 0, draw on current canvas. Virtual void rotate, int angle, equals 0. Virtual shape, destructor. Naturally, this interface is an abstract class. As far as representation is concerned, nothing, except the location of the pointer to the VTBL, is common for every shape. Given this definition, we can write general functions manipulating vectors of pointers to shapes. Void rotate all vector shape points to address of v, int angle, rotate v's elements by angle degrees. For auto p in v, for every element of v, from the first to the last, place a copy in p. P access through rotate, angle. To define a particular shape, we must say that it is a shape and specify its particular properties, including its virtual functions. Class circle, public shape. Public. Circle, point p, int r, constructor. Point center, const, return x. Void move, point to, x equals 2. Void draw, const. Void rotate, int, nice simple algorithm. Private. Point x, center. Int r, radius. So far, the shape and circle example provides nothing new compared to the container and vector container example, but we can build further. Class smiley, public circle, use the circle as the base for a face. Public. Smiley, point p, int r circle, p, r, mouth, null ptr. Smiley, destructor. Delete mouth. For auto p in eyes, delete p. Void move, point to. Void draw, const. Void rotate, int. Void add eye, shape points to s, eyes dot push back, s. Void set mouth, shape points to s. Virtual void wink, int I, wink I number I. Private. Vector eyes, usually 2 eyes. Shape points to mouth. The pushback member function adds its argument to the vector, here, eyes, increasing that vector's size by 1. We can now define smiley, draw, using calls to smiley's base and member draw, s. Void smiley, draw. Circle, draw. For auto p in eyes, for every element of eyes, from the first to the last, place a copy in p. P, access through, function, draw. Mouth, access through, function, draw. Note the way that smiley keeps its eyes in a standard library vector and deletes them in its destructor. Shape's destructor is virtual and smiley's destructor overrides it. A virtual destructor is essential for an abstract class because an object of a derived class is usually manipulated through the interface provided by its abstract base class. In particular, it may be deleted through a pointer to a base class. Then, the virtual function call mechanism ensures that the proper destructor is called. That destructor then implicitly invokes the destructors of its bases and members. In this simplified example, it is the programmer's task to place the eyes and mouth appropriately within the circle representing the face. We can add data members, operations, or both as we define a new class by derivation. This gives great flexibility with corresponding opportunities for confusion and poor design. A class hierarchy offers two kinds of benefits. Interface inheritance. An object of a derived class can be used wherever an object of a base class is required. That is, the base class acts as an interface for the derived class. The container and shape classes are examples. Such classes are often abstract classes. Implementation inheritance. A base class provides functions or data that simplifies the implementation of derived classes. Smiley's uses of circle's constructor and of circle, draw, are examples. Such base classes often have data members and constructors. Concrete classes, especially classes with small representations, are much like built-in types. We define them as local variables, access them using their names, copy them around, etc. Classes in class hierarchies are different. We tend to allocate them on the free store using new, and we access them through pointers or references. For example, consider a function that reads data describing shapes from an input stream and constructs the appropriate shape objects. Enum class kind, circle, triangle, smiley. Shape points to read shape, isStream address of is, read shape descriptions from input stream is. Read shape header from is and find its kind k. Switch, k. Case kind, circle. Read circle data, point, int, into p and r. Return new circle, p, r. Case kind triangle. Read triangle data, point, into p1, p2, and p3. Return new triangle, p1, p2, p3. Case kind, smiley. Read smiley data, point, int, shape, into p, r, e1, e2, and m. Smiley points to ps equals new smiley, p, r. ps access through add I, e1. ps access through add I, e2. ps access through set mouth, m. Return ps. A program may use that shape reader like this. Void user. std, vector shape points to v. While, cin. v.pushback, read shape, cin. Draw all, v, call draw, for each element. Rotate all, v, 45, call rotate, 45, for each element. For auto p and v, delete p, remember to delete elements. Obviously, the example is simplified, especially with respect to error handling, but it vividly illustrates that user has absolutely no idea of which kinds of shapes it manipulates. The user code can be compiled once and later used for new shapes added to the program. Note that there are no pointers to the shapes outside user, so user is responsible for deallocating them. This is done with the delete operator and relies critically on shape's virtual destructor. Because that destructor is virtual, delete invokes the destructor for the most derived class. This is crucial because a derived class may have acquired all kinds of resources, such as file handles, locks, and output streams, that need to be released. In this case, a smiley deletes its eyes and mouth objects. Experienced programmers will notice that I left open two obvious opportunities for mistakes. A user might fail to delete the pointer returned by read shape. The owner of a container of shape pointers might not delete the objects pointed to. In that sense, functions returning a pointer to an object allocated on the free store are dangerous. One solution to both problems is to return a standard library unique PTR rather than a naked pointer, and store unique PTRs in the container. Unique PTR shape read shape, is stream address of is, read shape descriptions from input stream is. Read shape header from is and find its kind k. Switch, k. Case kind, circle. Read circle data, point, int, into p and r. Return unique PTR shape, new circle, p, r. Void user. Vector unique PTR shape v. While, cin. v.pushback, read shape, cin. Draw all, v, call draw, for each element. Rotate all, v, 45, call rotate, 45, for each element. All shapes implicitly destroyed. Now the object is owned by the unique PTR, which will delete the object when it is no longer needed, that is, when its unique PTR goes out of scope. For the unique PTR version of user to work, we need versions of draw all and rotate all that accept vector unique PTR shape thus. Writing many such all functions could become tedious, so shows an alternative.